All right, 11.7 part 2. Last topic of the semester. I know everybody's sad. So just we're going to follow from what we talked about on Friday with cylindrical coordinates. Introduce a new coordinate system which we will use again quite a bit next semester. In spherical coordinates, we represent points with the coordinates rho, theta, and phi. And we'll talk about what each of these is. Rho is the distance between the point and the origin. And theta is, and we're going to say rho is greater than 0. So we don't let rho be negative. Theta is the same angle that we use in polar coordinates and in cylindrical coordinates. So and we're going to say in spherical coordinates, we'll draw a picture in just a second, that R that we talk about in polar and in cylindrical, R is greater than or equal to 0. So in spherical coordinates, we let our distance from the point to the origin has to be positive, and this R in the xy plane has to be positive. We don't let it be negative. And finally, phi is the angle between the positive z-axis and the segment between rho and the origin. So we're measuring from the positive z-axis. And we're going to say that 0 is less than or equal to phi less than or equal to pi. So phi goes from the positive z-axis to the negative z-axis only. So let's draw a picture. Take a look at what we're talking about here. So let's draw our familiar rectangular coordinates, and we'll draw in our spherical coordinates. So we have a point out here in space. So we say this is the point rho, theta, phi. I had an instructor when I was in college that always pronounced this angle phi, and so sometimes I think of him and I find myself pronouncing it phi instead of phi. All right, so we're going to have a segment between the origin and he was Egyptian, and we would talk about we had lots of arbitrary constants instead of arbitrary, and that word stuck in my head when we talked about arbitrary constants, and we talked about the Euclidean norm instead of the Euclidean norm. He was a very good teacher. All right, so this angle from the z-axis to this segment, the positive z-axis is phi. And if I project this, the point, I'm going to project this down onto the xy plane, like so. I want to do that in black color. And we'll do these parallel to the coordinate axes here. Oops. Well, I've never done that before. Like so. And I'm going to project this directly down onto the xy plane. So that's the projection of this segment down onto the xy plane. So this angle would be theta. The length of this segment in the xy plane would be r, or r from polar coordinates or cylindrical coordinates. And the length of the red segment is rho. So there's our picture of how we're thinking about our coordinates in spherical coordinates. And this distance would be x, and this distance would be y, and this distance would be x. And I'll extend my axis out here a little bit so I'm going to point so this line actually intersects. So there's our picture of spherical coordinates. Phi is between 0, 0, and pi. So we go from the positive z-axis to the negative z-axis. Theta can vary between 0 and 2 pi. We can go all the way around here. R is positive, always positive, and rho is always positive. And spherical coordinates are useful when we have some shape that has spherical symmetry about a point, and it's often very useful also when it has when we're representing something with circular symmetry about some axis as well. So sometimes cylindrical coordinates are a nice representation of something with circular symmetry, and sometimes spherical coordinates work just as well. All right, questions on our definitions. It's very nice to be able to visualize curves, surfaces in a different coordinate system than a familiar rectangular coordinate system. It gets us thinking in a different way and lets us relate to what we're talking about in a slightly different way. And I think it's nice to be able to kind of expand the way we think about these things. All right, let's look at our conversions. We can go through the conversions. We could go through the derivations. It all comes from using these right triangles to do our conversions. But they are not difficult, and the ideas behind them not difficult either. So spherical to rectangular. X is going to be rho sine phi cosine theta. So rho sine phi on our diagram would be r. So this is r cosine theta. Y is rho sine phi sine theta. And z equals rho cosine phi. And those, again, come from, I'm just going to skip back here, looking at these right triangles and finding r in terms of rho and phi, and this, I forgot to mark this, the length of that segment would be z. So there's our z, our x and our y and our z. So it comes from looking at these right triangles, just like I said. And then to go the other way, rectangular to spherical. Rho squared is x squared plus y squared plus z squared. So that's just like r in polar coordinates or cylindrical coordinates. We just have the third coordinate there. Tangent theta is still y over x. And phi, a little more complicated, is the inverse cosine of z over the square root of x squared plus y squared plus z squared. And that's coming from here. And we can also write some conversions from spherical to cylindrical and back as well. So if we wanted to convert from spherical to cylindrical, or vice versa, we could do those conversions. And we're saying again that r is greater than or equal to 0 for these. R squared equals rho squared sine squared phi. Theta equals theta, and z equals rho cosine phi. Not a difficult conversion there. And if we want to go the other way, and we're saying again r is greater than or equal to 0. Rho equals the square root of r squared plus z squared. Theta equals theta, and phi is the square root of, z over the square root of r squared plus z squared. So not difficult to convert back and forth from spherical to cylindrical either. So those are our conversions that we will use. Yes.
So it's still supposed to be inverse cosine.
Yes, should be inverse cosine. Thank you. There we go. So those are conversions, coordinate conversions. And they just, all of those come from manipulating these to solve for the variable that we're looking for. All right, questions on our conversions? Okay, all I want to do just look at a couple of examples of doing some conversions to spherical coordinates and talk about what the surface is. Okay. So, we want to convert to spherical. X squared, nice easy surface, x squared plus y squared equals z squared. So before we do our conversion, what kind of surface is this? So, Chalfant says cone. If x equals 0 in the yz plane, we get y squared equals z squared, or y equals plus or minus z. So in the YZ plane we have lines. In the XZ plane, when y equals 0, we get x squared equals z squared, or x equals plus or minus z. So we get lines in the XZ plane, so our trace in the coordinate planes are lines. Parallel to the XY plane, when z is a constant, we get x squared plus y squared equals a constant, which is circles. So we get circles, larger and larger circles, parallel to the XY plane. So we have a cone. This would be our double naped cone. All right, so let's do our conversions. X squared, so x squared in spherical coordinates is going to be what? We're going to start a rho squared.
Equals x squared plus y squared.
So we want to write this in that rho squared does equal x squared plus y squared plus z squared. But we want to convert this to spherical coordinates. So x in spherical coordinates is, there we go, sine squared phi cosine squared theta plus y squared. So we get a rho squared sine squared phi sine squared theta equals, and z squared, rho squared cosine squared phi. And we can clean this up a little bit. So let's factor out this rho squared sine squared phi. That looks nice. So this is just 1, so I get rho squared sine squared phi equals rho squared cosine squared phi. And how can I simplify this? Sine squared phi equals cosine squared phi. And how can I simplify that? Tangent squared phi equals 1. Oops, thank you. Or tangent phi equals plus or minus 1. What phi gives us a tangent of plus or minus 1? Pi over 4. 3 pi over 4. Between 0 and pi. So the equation for a cone in spherical coordinates is phi equals a constant. And that constant, that tells us the angle that the sides of the cone make with the z-axis. So isn't this phi equals pi over 4? Much easier to work with than x squared plus y squared equals z squared. So the equation of a cone in spherical coordinates, very simple. Isn't that nice? Questions there? Phi equals pi over 4. How much nicer could that get? Okay. Another example. We're going to convert to spherical. X squared plus y squared plus z minus 1 squared equals 1. So what is this surface? Any ideas? What would the surface x squared plus y squared plus z squared equals 1? What would that be? Sphere, radius 1, center at So the x squared plus y squared plus z squared would be centered at 0, 0, 0. So this is going to be a sphere, radius 1, centered at 0, 0, 1. So before we do this conversion, in spherical coordinates, what would be the equation of a sphere of radius 1 centered at the origin in spherical coordinates? Rho squared equals, or just rho equals 1, right? We just have that radius equals 1, so that would be our equation for our sphere in spherical coordinates. This one we have the shift, so it's a little more complicated. So let's plug in our conversions. So we're going to start like we did on our last one. So we have rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. So we're going to have a similar situation here. Plus now we have the z minus 1. So this is going to be rho cosine phi minus 1, square that, and that equals 1. So we know that we just simplified this to rho squared sine squared phi. And now we're going to expand this, plus rho squared cosine squared phi minus 2 rho cosine phi plus 1 equals 1. This is looking fairly nice, right? Rho squared sine squared phi plus rho squared cosine squared phi simplifies to what? Can factor out the rho squared sine squared phi cosine squared phi. This gives me 1. So I get rho squared minus 2 rho cosine phi equals 0. Factor out the rho. Rho times 1 minus 2 cosine phi equals 0. Are we going to lose anything if we... What did I do? Rho, yes, rho minus, there we go. Am I going to lose anything if I say that rho is not 0? If I just ignore this solution or divide by rho? On that sphere, is rho going to be 0? No. So I can divide both sides by 0. I'm not losing a solution. So I'm going to say rho equals 2 cosine phi. And we're saying rho is not equal to 0. So the equation for this sphere in spherical coordinates is rho equals 2 cosine phi. So again, this is easier to work with than this.
Would there be a point on that sphere where rho equals 0?
So there would be a point. There would be a point. Would that solution come out of here?
Yeah.
Yeah. So we're not losing a solution by saying rho is not equal to 0. So we're here. I'm saying that I'm assuming the rho is not equal to 0, so I can divide out that rho. But this would give us rho equals 0 also. So I guess we could leave this condition off. Is that what you're saying?
Yeah.
Yeah. We could leave that condition. I guess I could put it up here that we're assuming that rho is not equal to 0 because we're not losing a solution. As long as we don't lose a solution by dividing by rho, we're okay. So be a little more precise. Okay, questions on that? Spherical coordinates for certain shapes are very, very, very nice to work with. And we'll be using them quite a bit second semester. Okay. There you go.